Alright, so here we go. I kind of lied a little bit. This example is not that great, but maybe it's a little bit interesting because it's a little unexpected. You've got a bunch of x's and square roots and whatnot, and I think it's good for us to practice a little trig stuff. So suppose you make this your substitution. You got x's and u's. This is the beginning of your dictionary. This is the creative part, the part you have to invent or imagine or copy from somebody. The rest is not that imaginative. You just do the differential. So I have a dx is equal to, oh, you know what? I'll show you a little trick here for free. I wasn't going to include this one, but I'll include it for you for free. If I have x to the 1/2, that's the same thing as tangent u. That saves me from having to do chain rule here on a square. So now I slap a d on both sides. So I have the half x to the negative 1/2 dx is worth a secant square u du. Just, I don't know if it adds a little bit. Sometimes that's helpful. Alright, I could rewrite this also this way. The square root of x is equal to tangent u. That's a rewrite of the first line. Alright, all this is still part of my imagined, created, or copied dictionary. Alright, let's get to work here. We need to make our substitution. Give ourselves a little room here. Substitution on the top. I'm gonna put square root of x dx. So square root of x. I gotta make some substitutions. So x is equal to tangent square. So I'm gonna go with tangent square u plus 1. That's what goes on the bottom, and this is squared. The dx. I'm gonna go to my dictionary and figure out what's the exchange rate for a dx. The exchange rate for a dx would be a secant square u du divided by 1/2 over the square root of 1/2 over the square root of x. Right, that's what you divide over here. So you could flip that over to the top, and that becomes let me see, that becomes 2, and I could pull that 2 when you flip it up to the top. The square root of x, you could flip it up here and it becomes x. This is famous, the tangent square u. The tangent square u can be exchanged for secant square u. And of course that is squared. That takes care of a bunch of these pieces, and I have secant square u du. And that's alright. I still got x's here, which is good because otherwise the fun would be over. So I'm going to go back to my dictionary and substitute in my x's. And that becomes 2 integral of tangent square u all over, I can cancel one of these secants, so it becomes secant square u, because I have 2 here. That would make 4 of them, but 2 of them get cancelled, and I have a du here, right? And then what can we do? Well, could do so many things. This becomes 2 integral, maybe I could use some famous identities here. Secant square u minus 1, that's the same thing as a tangent square all over secant square u du. Then I can split this up into a couple of fractions. So that becomes 2 integral of secant square u over secant square u minus 1 over secant square u. All that times du, and I can split this up into a couple of different fractions. I have 1 minus cosine square u. This is a 1, this is a 1 minus, and that becomes du, and of course that's famous. That's a sine. That is the craziest sine. Sine square u du, and of course that's a famous one. Famous technique for integrating that. Maybe use an identity here. 1/2 minus 1/2 cosine 2u du, and then this becomes easy to integrate. That becomes 2 1/2 u minus 1/4 sine 2u. Remind me later. That's times du. And now I could put the 2 back in there if I wanted to. That would become 2, well no, that would just become a plain u. So that would become u minus 1/2 sine of 2u plus a constant. Now you're done, except that it's customary to answer in the same way that the question was posed. The question was posed with x's. It would be polite if we answered with x's, not with u's. So you go back to the dictionary and you try to figure out what the exchange rate is for each one of these. U, I'm looking at U, it would probably be an arc tangent of square root of x. So I'm going to go with arc tangent of the square root of x. That's my U from the dictionary. Minus 1/2. Oh my goodness, what are we going to do here? Sine 2u. I don't even have 2u's here. I have single angles. And I have double angles here. What I could do is maybe use some trig identity to switch my double angles into single angles. I know a famous one. The famous one would be that this one is 2 times sine u cosine u. This one's equal to 2 sine u cosine u. So the 2 and the 1/2 would cancel, and so this becomes sine u cosine u plus a constant. And now what? I don't even have those in my dictionary. So this is what I was saying before. Sometimes in the part of the dictionary you may need a right triangle to figure out what the exchange rates are. So this tangent is a ratio of opposite to adjacent. That means if I was to draw a reference triangle with u as one of the angles, the opposite side would be square root of x, the adjacent side would be 1. At least that would be the ratio. Square root of x to 1. That's the only way you can get the tangent of u to be square root of x. You can use Pythagorean theorem here a little bit to figure out the other side, x plus 1. And now I can look at this triangle, I can easily figure out what sine of u is. And I can easily figure out what cosine of u is. So this becomes arc tangent of the square root of x minus sine. Sine would be this ratio, so it would be the square root of x over square root of x plus 1 times cosine. Cosine is this ratio, 1 over the square root of x plus 1 plus a constant. What can I say? Maybe I have one thing to say. This. What? What? Dumb applause is not. Haha. Alright, we'll see you guys here next time. Next time we're really going to step it up a notch or two. This is an alright example, but it gets a lot better than this.